Welcome to my talk, Closing the Loop, Dynamic State Estimation and Feedback Optimization of Power Grids. My name is Miguel Picallo, and this is a joint work with Saverio Bolognani and Florian Dörfler. There are many examples of optimization and control in power systems. For offline optimization, which consists on solving a problem to take complex decisions, we find an example in the day-ahead plan to dispatch based on forecast. An example for online control, which is fast, model robust, and measurement driven, is, for example, in the primary and secondary response for frequency balancing. So those are two examples of separate optimization and controlling power systems. But what about, for example, rescheduling, the redispatch of set point and voltage regulation? Due to the increasing unpredictable and time-varying conditions caused by the increasing amount of renewables and the unpredictable loads, the cost of rescheduling is increasing. However, we have to our advantage an increasing number of fast response power electronics and a more available sensor and communication network, which can help us to lower this cost and perform better. So the key is how can the advantages of offline optimization and online control be combined to create an online measurement-driven optimization that would be able to track the optimal power flow solutions in real time. In the context of distribution grids, there are even additional challenges. The integration of renewables is much higher there. So the share of renewables over traditional generation is higher. Also, apart from these unpredictable renewables, fast time varying demand in the loads also causes these sudden changes. Moreover, the models in distribution grids are less accurate, and there is a scarcity of sensors and actuation. In this sense, such an online optimization could be helpful to mitigate these uncertainties and fluctuations. Now, if we consider the set points of the controllable power injections as inputs, the node voltages as the state of the system, and the uncontrollable loads and admittance matrix as parameters, we can define the AC optimal power flow as follows. The objective is to minimize the operation costs, some function of the power injections, and enforce grid constraints, like voltage violations, while satisfying the steady-state grid AC power flow loss and the available power capacity. That means, for example, that the power from the power injections has to be between a lower and an upper threshold. To solve this problem, online feedback optimization is a recently proposed approach which has attracted a lot of interest, and it can be used to solve the AC optimal power flow in real time using measurements. It consists on taking measurements of the node voltages from the physical system, updating the set points of the power injections, saturating these set points in order to satisfy the power capacity, and send the set points back into the physical system. This approach has several advantages. For instance, it produces feasible inputs, feasible power set points at all times. It doesn't require power flow computations, only measuring these node voltages V. And in the sense of a model, it only requires the sensitivity of the voltages with respect to the power injections, such that it's more robust to model errors and time-varying conditions. More importantly, there are some conditions, it can be proved that this approach converges to the optimum of the AC optimal power flow with time. However, there is an underlying strong assumption in all these approaches, which is that the node voltages V, the ones that we want to control, are all measurable. But what if they are not? For example, in distribution grids, where the measurement scarcity may render the system unobservable and not all the voltages, all the node voltages may be measurable. In that case, we need something like an online state optimization to keep track of these node voltages. Now, how to build such an online state estimation? If we consider all the measurements we have available from different sensors, like SCADA measurements, smart meters, phasor measurement units, etc., even with those measurements, which can be of different sorts, we may have that the system is still unobservable due to the measurement scarcity. To compensate that, we can use pseudo measurements, which are inaccurate load predictions created using the average or nominal load profiles plus a high variance node. With these measurements together, we can make the system observable and use a Kalman filter to create a dynamic state estimation that is able to handle uncertainty in the measurements. Such an estimator would take the noisy measurements as input. It would update the state estimate and the covariance of the state estimate using these update rules, and it would produce a state estimation B hat. Back to the online feedback optimization scheme, the state estimation would fit as follows. Now, from the physical system, we would receive the measurements. The state estimation would update the current state information based on these measurements to produce a more updated state estimate. This state estimate would be sent back into the system here to update the set points. These set points then are saturated to satisfy again the power capacity constraint and sent back into the system, and the state estimation such that it can take into account the update of the set points. Again, this approach has some of the advantages that the previous online feedback optimization without state estimation had. For instance, this also produces feasible inputs at all times. It doesn't require power flow computations, only the measurements Y. And very importantly, it does not require to measure the full node voltages, but only the measurements Y. Again, it only requires the sensitivity of the voltages with respect to the power injections, so that it's robust to model errors and time-varying conditions. However, it's not clear yet whether this interconnection of state estimation and online feedback optimization converges and is stable around the optimal. Why? Because the including of a state estimation, which has its own dynamics, could hurt the dynamics, could hurt the convergence and stability of the whole system. To answer that question, we have the following result. Under some conditions, namely that the cost functions f and g are L smooth, that the cost function f is mu strongly convex and g is convex, that the measurement matrix H is full column rank, which is true if we consider pseudo measurements, that the noise covariances sigma L and sigma Y are bounded, sigma Y is full rank, and the covariance of the state estimate is lower bounded, we have the following theorem. First, there is a separation principle. So the Kalman filter and the gradient descent optimization from the online feedback optimization, they can be designed independently. Second, if we choose a small enough step size in our online feedback optimization, this interconnected estimation optimization converges and is stable. Converges in the sense that the norm of the expectation of the estimation error and the optimization error both converge to zero. And there exists two constants, CV and CS, such that the expectation of the norm of the estimation error and the optimization error, it converges to a value less than infinity. So a value that is bounded. Why these two are different in the sense that the expectation and the norm change places. In a sense, this is saying that the bias estimate that the bias of the estimate and the bias of the optimization is going to zero, but that the covariance of the estimation and the covariance of the optimization error go to a value that is bounded, which means that is less than infinity. We have tested this approach in a simulation using the IEEE 123 bus test feeder, which is a three-phase unbalanced test feeder. As consumption data, we have used 1-second resolution real household load profiles, so that it's a fast time-varying consumption. We have used real solar radiation and wind speed data to simulate distributed generation in certain nodes of the network. And we have put some measurements in the network, but not enough to make the network observable. These measurements have low uncertainty, but they need to be complemented with pseudo measurements, average load profiles, which are highly uncertain. The first thing we observe in the estimation is that it converges very quickly to close to zero and remains close to zero. So the estimation converges very, very quickly. The optimization does not converge as quickly, but still converges, even in time-varying conditions. We can see from the maximum port available here that the conditions are changing, but we can see as well that the distance, the error between our set points and the optimum go to zero. And our proposed set points are able to track the optimum, which uses all the information. Additionally, we can see that the voltage is within the limits almost all the time. There are small violations here, which may be due to the uncertainty captured in the covariance, but still it mostly remains within limits for all nodes in the network. As a conclusion, we can say that in our scheme with the online feedback optimization, the physical system, and the state estimation, with this scheme, we are able to monitor and optimize and control the unmeasured states. Moreover, we are able to prove that this interconnection of estimation and optimization converges and is stable around the optimum. And we have also successfully tested this approach in simulation. As future work, we would like to consider nonlinearities in both the power flow and measurement for the proof of convergence and stability. We would also like to consider unbiased noise, like low trends in the prediction, meaning like one would be in the case that the load would be following a trend that we can predict, and we can use that information also to perform better. Moreover, to avoid some of the violations that we had in the voltage, we would like to consider also a chance constraint optimization, which could use the estimation covariance as extra information to satisfy the voltage limits even better. That was all in my presentation. Thank you very much for attending, and I would like to answer any other questions here.
Perfect timing again. So thank you so much, Miguel, for this interesting presentation. I don't see any questions. So while they try to encourage questions, I have a couple of questions for you. The first one is, what about the robustness of the overall stability against bad data? I mean, you may have outliers in the measurement. Can they destroy the convergence, or?
No, but that's a very interesting question, actually. In this case, since we already had only a very few measurements, it's also very hard to address them, to identify bad data, because mainly you don't have enough measurements. You don't have the redundancy here. So in this case, these bad measurements, this bad data, they could hurt the convergence of the whole combination quite badly. Yes.
Okay.
Basically, the question to answer here would be, how can we perform bad data analysis in a scenario where we have only few measurements?
Well, so it's a bit more complex probably, because, it's a colleague of us, Lamin Mili, and his students who have been working with robust state estimation, who are,
yes,
capable of addressing a situation to, leverage point and this kind of thing. So this is a little bit more complicated, but
Definitely, yes.
Another question is why would you use a regular static state estimator instead of dynamic state estimator? Would be useful?
The key point here is that we are combining the estimation with the optimization, right? And basically this optimization is causing some dynamics in our system. This causes that a static estimation would not be able to predict what's going to be the next state given the change of the inputs in this case. So that's why we preferred a dynamic estimation in this case, because then we can capture this this change of the states due to the change of the inputs.
Okay.
We're actually working on an extension of this paper where actually it's much more complex the way you need to take into account these dynamics due to the optimization.
Yeah, also the non-linearities as you were suggesting.
Precisely that, yes.
Feeder and passative constraints are very important because I'm not strongly non-linear. There are a couple of questions by Patrick Pansepisi and say, Greg told, how do you estimate the noises covariance, sigma, sigma y, sigma I? I believe that these estimates are critical.
Yes, that's completely right. Estimating these covariances is a critical issue. And here we were just using past data to estimate these covariance, but actually another, let's say another word that we are kind of like working at the moment is how to be distributionally robust. Meaning, you suppose that your data is around a certain distribution, but might not be there. That's actually very helpful for pseudo measurements. And then basically you are robust around that distribution in an infinite space, and you kind of like you protect yourself against the worst case of these covariances.
Another last question by Dan Molson is, thank you, Miguel, for the interesting talk. To clarify, do your results characterize how accurate your measurement had to be to achieve a given tracking accuracy of the OPF solution?
That's a very good question. We didn't include all the parameters there in the presentation, but they are in the paper for anyone that's interested. And yes, so those parameters that that affect the stochastic stability of the optimization and the estimation, they depend heavily on the covariances of the measurements and the loads. Which means if our measurements are more accurate, we're going to be able to track the optimal much better. If they are less accurate, we are going to be tracking them much less accurately. So yeah, there's a very clear correspondence between these bounds and the accuracy of the measurements.
Thank you so much, Miguel.